we have the PV equals nRT equation, but that doesn't always happen in real life, okay? It doesn't happen at every condition. It performs perfectly when it does happen with no attraction between the particles, but ideal gases don't exist because it's very difficult to achieve that. So even so, at many conditions of pressure and temperature, a real gas behaves very much like an ideal gas, where real gases differ from an ideal gas at low temperatures and very high pressures. There's an equation that goes along with this, but it's very complicated, so we're not going to do that in Chem 1. So Dalton came up with something when we have a mixture of gases. Gas pressure depends only on the number of particles in the volume and their average kinetic energy. So particles in a mixture that have the same temperature have the same average kinetic energy. They're moving around the same amount. The contribution each gas in a mixture makes to the total pressure is what we call partial pressure. So to find the total pressure, you just add up. You find the sum of the partial pressures of the gases. Okay? So Dalton's law of partial pressure states that at constant volume and temperature, the total gas exerted is equal to the sum of the partial pressures, where however many gases you have in a sample, you add those all together, and you get the total from that. So, for example 7, we're going to do just that. Air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What's the partial pressure of oxygen at 101.3 kPa of total pressure if the partial pressures are there listed? So, let's figure out how many gases we have first. So we have our total pressure is equal to, well, we have oxygen, nitrogen, carbon dioxide, and then trace amounts of others. So I'm going to put the partial, I'm going to still use P for pressure, and then I'm going to put the chemical substance down a little next to it. So that's of the oxygen gas, and the partial pressure of the nitrogen gas, plus the partial pressure of the carbon dioxide, and then the trace amounts of others just means that they're so small that you just add them all together. So I'm going to say P of other there. Okay. Well, now it's asking us to solve for the partial pressure of PO2. So I'm going to leave that as is. And then we're given that we have 101.3 total kPa. So that's going to be my P total. And then these numbers after, at the end, respectively means in order of how they're listed. So the 79.10 goes with the nitrogen, the 0.040 goes with the carbon dioxide, and the other is the 0.94. So how do we solve for P2? Well, we add up the right side, and then we're going to subtract it from the 101.3. So the partial pressure of oxygen gas with correct significant figures is going to be 21. And our unit is going to be kPa, because these were all in kPa. Okay? Pretty easy stuff. That's actually going to be a bonus question on the test, because it is so simple. Diffusion is the tendency of molecules to move towards areas of lower concentration until the concentration is uniform throughout. So this is the movement of gases. It's how, like, when somebody passes gas, if you're right next to them, you smell it, but far away, you don't. But maybe if you're, like, in a car, then it spreads out so everybody can smell it. So that's just the tendency to move until everybody can sense that the gas is there, or smell it if you're in the car. It's a relatively slow process, but it still happens. So we have a lab that helps us with that. Effusion happens when gas escapes through a tiny hole in the container. So with effusion and diffusion, gases with lower molar mass have more movement or move faster than gases with higher molar mass. And that's because the smaller molar mass allows them to move more quickly than the bigger molar mass. Or in the fusion's case, if it's going through a hole, maybe there can be 2 or 3 small molecules going through compared to one large molecule. With these, we have an equation, the Graham's law of effusion, which also can be applied to diffusion. It is correct in your notes, don't worry about that, where it has this ratio, okay? One thing I want to point out, we're never going to actually just solve for rate A or rate B. We're just going to solve for the ratio, okay? And another thing, whenever I set this up, A and B, so you're going to be given chemical compounds and you plug in molar masses and then solve for what the square root of that is. I always put the bigger on top because then that makes a nice, more whole square root of whatever the number is. Okay? So let's try the example 8. How much faster does helium fuse than nitrogen at the same temperature? So we're going to solve for the ratio. Okay? So underneath my square root sign, I'm comparing helium, which is not a hunk of fiber, versus nitrogen, which is. Well, helium has 4.003 as its molar mass, and nitrogen, one of them is 14.007, so two of them is 28.014. 28.014 is bigger, so I'm going to put that on top. And then the 4.03003 will go on the bottom. Okay, well, to simplify, that's going to be about the square root of 7-ish, right? Well, then, to actually solve it out, we're not going to leave it in square root terms. We're going to actually solve for the answer. That would be about 2.7. There's no sig figs here, so it doesn't really matter what you round to, but you can just pick a whole number, a couple decimal places, whatever you want. So, that's it for chapter 14. Good luck. Make sure you do the chapter review.